Yeah, good. Yeah. Okay, got it. Okay. Good evening and good day, ladies and gentlemen. My name is Bob Hugh. I'm your host for this evening and today's webinar. I'm a board member of Alberta AI, and I'm also the Vice President of Business Development with the Data Management Association of Edmonton, another professional and nonprofit organization. It gives me a really great deal of pleasure to introduce our speaker, who is an AI technology specialist based in Edmonton. Bruce Matichuk has been working with AI since the 1980s and has successfully deployed projects in many large organizations such as Liberty Mutual Insurance, Lockheed Martin, and Hallmark. He built a chat system for AOL in the mid-2000s and was the senior technologist responsible for building a conversational system for getting directions at point during the startup years. Bruce was also a co-founder of Aiden Technologies, Inc., where he successfully built a face and behavior recognition system. He now works with HealthGauge, building an intelligent health monitoring and management platform. Bruce received his MSc in computer science from the University of Alberta, where he is currently completing a PhD in AI, focusing on neuro-symbolic systems. Bruce has patented many of his AI inventions and has co-authored several papers on AI. He is also a sought-after speaker on AI in conferences and webinars. With the title, Machine Learning Blood Pressure Estimation, ladies and gentlemen, please help me welcome Bruce Matichuk. Bruce?
Great. Thank you, Bob, for that very excellent introduction. So what I'm going to talk today a little bit about is HealthGauge and what we're doing to use artificial intelligence to estimate blood pressure. So first I'll talk a little bit about the company. I'll talk a little bit about the company. So who we are, we're a digital health solutions platform. And what that means is it's an extensible platform where people can add components into our network. What we do is take data from devices and we bring that data up into the platform, allowing people to capture their data, monitor it. We provide analytics. The overall goal is to allow people to improve their health outcomes while reducing costs to the healthcare system. So extensive research has shown that if you monitor your health on a regular basis, that you can actually improve health outcomes. You basically make yourself healthier, and this can reduce the cost for yourself and the health system in helping you to be healthy. So just give you one example, rising health services costs due to heart disease. So there's in North America alone, and this is a worldwide problem. In North America alone, there's 100 million people that are affected. There are 1.5 billion people affected worldwide. And it costs, just in the USA alone, 400,000 deaths related to heart disease. And it's a massive cost to the health system. And really all that's required to address a lot of these issues is regular monitoring. You should, what the American Heart Health Association says is if you just measure yourself a few times a day and then take steps when you have hypertension, that you can significantly improve your quality of life and your length of life. So this is a little bit about what our platform looks like. We take sensors, those sensors go into applications. We have an application called HealthGauge. It monitors various kinds of conditions. That goes up into a cloud, and in the cloud, we do machine learning training on the data, and we produce various kinds of machine learning based analytics. And that data can be shared with you, or it can be shared with your doctor or health professional or other people that are interested in that information. So we sell these devices. So I'm wearing one right here, and it can actually track all this, the various kinds of things I'm pointing to right here on the screen. It uses Bluetooth to talk to the smartphone, and then it's got HR or heart rate variability. We detect blood pressure, electrocardiogram, photoplethysmogram. We track other metrics as well, sleep, activity, and all of that goes into a journal and then gets analyzed online. But what I want to talk about today is HealthGauge AI and a specific application of machine learning to do something called blood pressure estimation. So this person is getting up, all she's got that watch. So how do we go from a reading off of a watch to a blood pressure estimate? If you ever had your blood pressure taken before, you know that it's kind of painful. A little cuff goes around your arm, squeezes your arm. So what is it doing when the cuff is squeezing on your arm? What is it trying to measure? So this is a little graph showing you what is actually happening with what's called the oscillometric method, which is one way of reading your blood pressure. There's a little microphone in there, and it listens to your heart beating, and it squeezes your arm until the blood gets cut off and it can't hear the heart anymore. And that's going to be your systolic blood pressure level. And then it releases the pressure until it can actually hear the heart again, and that's going to be your diastolic level. And so those two metrics represent the systolic and diastolic blood pressure. So how can we take a watch, and all that exists on this watch is an ECG monitor, electrocardiogram, which measures the electrical activity of your heart, and a PPG. So at the back of this watch, there's a little LED that shines light into your wrist.
Sorry, Bruce. I'm sorry to interrupt you. Yeah, since your slides did not move, we are just seeing your first page. Could you please switch it to display mode?
Okay.
Okay.
You're just seeing the first slide?
Page. Yes,
Yeah,
first slide.
just seeing the first slide. Yeah.
Can you see this slide now too?
No.
Okay.
Maybe you can share it again. Restart the share.
Oh, here we go. Yeah. Okay.
Yeah, now it's working.
Now you're on the second slide. Okay, advance to this third slide.
Okay, so I'm gonna go into presentation mode. Can you see this second slide now?
No.
Oh, really interesting.
Okay.
Okay.
I can only see research group. Well, there we go. We got a second slide.
All right.
Okay. Yeah.
So basically the problem is that when I go into presentation mode, okay, how does this look? Does this look okay?
Yeah. Oh,
all right.
Yeah. Okay. Yeah.
So I'll start again. Who we are. We digital health solutions platform. We capture data, monitoring and analytics to prove health outcomes. So this is just showing that research shows that we can improve our health by monitoring. And then I was just going over this slide to show this is a major problem in health in general. So this is our platform slide. And what this shows is that we have devices. These are the devices on the left. They go into our applications. And then our applications, all the information goes up into the cloud. And we have machine learning systems in the cloud that can actually assess the data sitting in the device. And then that information then goes to you or goes to your health provider to share your data. So this is what we are selling. So devices, software, and the cloud. So I was talking about the oscillometric device. So here's a picture of somebody using an oscillometric device. You can see it squeezes the arm. And this was the graph showing what's actually happening when you actually take an oscillometric reading. So the cuff squeezes up to a certain amount of pressure, and when the heart when your blood flow is completely cut off, that represents your systolic blood pressure, and then the pressure is released, and when the blood starts flowing again, that represents your diastolic pressure. So this is a picture here of our watch, and the watch has an ECG electrocardiogram, and it has a photoplethysmogram. So how do we go from those measurements to actually a blood pressure measurement, measuring the actual pressure in your wrist? Well, what we can do is we use something called machine learning, which you all know about. For those that aren't as familiar about machine learning, I'll just talk a little bit about what that is. The bottom diagram here shows you what are called neural nets as input. And in our case, these individual inputs represent different points in time on these sensors, electrocardiogram sensor or a photoplethysmogram sensor. And then what you can see the neural net is doing is it's processing that information in layers, and to the final layer where it actually makes a decision about what the output reading should be. So there's a few other things that happen. The diagram up here shows you convolutions. So it actually looks at different parts of the signal and process different parts of the signal. And you can see that's actually a multi-dimensional signal, many dimensions. And these dimensions are reduced at each layer in the network until you end up with a final classification layer. And the final classification layer represents your output. So, so the problem in blood pressure estimation is how do we convert these signals from, something that looks like this. On the top, I've got what's called a photoplethysmogram. On the bottom, I have an electrocardiogram. And what I want it to look like this on the right, where it actually provides an output. So the first thing that we have to do, obviously, is get some training records. So we take a bunch of blood pressure readings with our device. Those blood pressure readings are correlated using an oscillometric device that gets stored in a database. And that's now our ground truth. And the neural net can then look at that data and come up with an analysis method. So the first thing that we have to do is we have to, am I online?
Yes, you are, Bruce. Yeah.
Okay. My camera froze there. So, okay. So the first thing that we have to do is we have to process the data. And so what we do is we filter the data. We do what's called a low pass filter, and we do a high pass filter. So this is what the raw signal looks like coming off of the watch. It's kind of like all over the place, but there's a lot of information there. Once we apply the high pass and low pass filters, the information becomes usable for the neural net. When we look at that data, what we can see is that there's problems with the data. There's different parts of the signal that actually don't make any sense. So what we have to do is train the neural net to ignore the parts of the signal that don't have information. And that's part of the data cleansing and also part of the training process. The other thing that we do is we normalize the data. So these bumps, if you like, or the signal itself is variant, and so we have to equalize these heights in order to come up with good readings for the neural net. The other thing that we do is we analyze what's called the pulse transit time. There's tons of research that shows that if you look at the starting pulse of the ECG, which is the R wave here, and the rise in the systolic peak, so this is the PPG, that this distance right here contains a lot of information. So what we do is we calculate this transit time and we use that as an input into the neural net. Now, early on, we did a lot of work processing systolic width and diastolic width, which are these measurements over here. So this is the systolic side of the pressure wave. This is the diastolic side of the pressure wave. And we did a lot of work looking at these widths and various metrics. And that actually turned out to be a fairly decent neural network. And I'll just show that in a second. The other thing that we do is we take into account age, weight, height, and gender, and we add those into the neural net. So overall, what we end up doing is we end up taking the entire signal and we take a window into the signal and we window over the data, which means we take a section of the data and then we do some analysis on each one of those windows. And I'm gonna just flip over to this side. So then for each window, we figure out what the outliers are, and then we take the other windows and we average the results from the neural net. And so that's how that windowing works. So originally, our first attempt was to do pre-computed features, took the raw PPG, and we just extracted all of these features from the PPG. We then put that through a dense layer that looked like the neural net that I showed you right at the start. And that produced results, but they weren't that great. So then what we did is we went to a different model, and this is the current model that we're using. So we take the raw PPG and the raw ECG signals, and those go through a one-dimensional convolutional neural net. What we do then is we do dropouts. So what dropouts are basically picking different parts of the neural net and just dropping out those values. And then max pooling, where what we do is we compress the information into fewer neurons. That's the best way to describe it. Because the input signal is going to be around 1,000 inputs, and then that has to get reduced down to a single input as output. Sorry about that. So now what we do is so the results from this particular neural net turn out to be incredibly good, as effective as a blood pressure cuff. So this is a Bland-Altman plot of the results. In the Bland-Altman plot, we can show that 95% of our data is fitting into this plus or minus 2 standard deviations from the mean, and which basically means that our device is comparable to an FDA regulated device. So what we can see is that there's some bias, and the bias is towards records that we have a lot of records. So we have a lot of data in the normal range. We don't have enough data in the outer ranges. And so to reduce that bias, what we're actually doing is something called ensembles. So what an ensemble is you actually generate more than one neural net by doing random sampling. So in the bagging technique, we generate a neural net by doing random sampling, and then we do that again, and then we do that again, and then we end up with more than one model. And so then what happens in the ensemble technique is that these models will vote, and that turns out to be a very effective way to boost the value. There's also something called adaptive boosting. So we apply adaptive boosting to our neural networks. So the way that adaptive boosting works is we take a sample of data and we generate a neural net. And then what we look at is the data that's lower frequency. we sample data that's of lower frequency more often. And then we develop another neural net, another result. And then we do that again. And then what we do is average these results. And that gives us a boosted value. So if you look at the results, what you can see is that we're incredibly accurate for data that we have a lot of measurements for. Error goes up for data that we don't have a lot of measurements for, but the boosting definitely reduces the error. So you can see that these error bars over here are affected by the boosting technique. So, so this is a Bland-Altman plot after the boosting technique. And what you can see is that our standard deviation has improved substantially. And we're getting, incredibly good results with this particular technique. So there's some limitations to what we're doing here. So one of the limitations are that we don't really have enough data in the central areas. In the outer areas, we have too much data, if you like, in the normal area. I shouldn't say too much. We can always use more data, but the data in these areas produce really, really good results. So as we collect more data, this particular technique is working really, really well. So there's some problems with poor data labeling, and that can create errors as well. So some of the challenges that we face is that there's a lack of diversity in the data. So we don't have enough female data. We don't have enough young people data. We don't have enough, and this can really skew the results. And so this is some of the studies that we're doing will actually get us more data and increase the accuracy. We also have a bit of limitation in terms of the high data as well as the low blood pressure data. And sometimes people input inaccurate personal characteristics, which can affect the readings. So that's that's basically the core blood pressure analysis side of what we do. What we're doing as well is we're trying to make better use of limited data sets, and I'll talk a little bit about what we're doing there. So as you know, machine learning is really good in areas where you have data, but it's not that great at projecting when you are missing information for areas where you don't have good data. It does some projecting. The question is, how bad is it, or how much off is it for these other areas? And so how can we deal with this problem? So we apply Bayesian deep learning techniques to do some analysis of this problem. So this is a really useful graph to just show you that in areas where you have a lot of observations, the estimate, which is this line kind of running through the middle, that estimate is really, really accurate. But in between these lines, you can see there's many different possible curves that could follow through those observations. And so you're less confident in areas where you don't have a lot of observations. So the question becomes, well, is there a way after you've built a neural net to determine how confident you are of individual measurements? And it turns out that what you can do is use this dropout technique. And so what the dropout technique allows you to do is to you build the entire neural net, and then you do an assessment. And then what you do is just drop out some of the neurons in the network, just random ones. And then you do another assessment. And then what'll happen is, if the network is not very certain about that particular measurement, there'll be a lot of variance in the output. But if the network is really, really certain, you'll have small amounts of variance. And what that will allow you to do is basically determine, by just taking a bunch of samples, determine the level of certainty that you have for those analysis. So the other thing that I wanted to talk about is boosting the data set using something called synthetic data. So if you've ever heard of synthetic data, this is a new emerging technique that allows you to generate more data to improve your neural net. And so I'm going to talk a little bit about what's called GAN, or generative adversarial networks. So if you haven't seen this before, this is pretty interesting stuff. You have a generator, which is a neural net that generates fake signals, and you have a discriminator that tries to discriminate between fake signals or real signals. And these two networks are in opposition to each other. The generator tries to, if the generator gets found out by the discriminator, then the generator has to improve. If the discriminator makes a mistake, and then the discriminator has to improve. And these things work together to become very intelligent over time. And so here's an example of the GAN technique applied to faces. So in this particular case, the question here is, which one of these is fake? Well, if the answer, it's a trick question because they're both fake. And what you realize is that these GAN techniques are so powerful, they can create data that looks completely real. And we use this technique to generate fake data in order to facilitate machine learning. And we generate a whole bunch of fake data. It's called synthetic data, and that's what this area really is all about. You can see this is what the generator does. The generator starts from random vectors. These random vectors build up into high-level full images. And then we have the discriminator takes these full images and reduces them down into some evaluation. So this is how we generate fake data. So we've given a name to this network. We call it the BioGAN network. And you can see this is how it's structured. On the left, at the top left, you can see this is we can see we generate, we decode, we then come up with output, and then that goes through the discriminator. The discriminator then is basically doing the job of, say, blood pressure analysis. Or this same technique can be applied to any kind of data that you might want to generate. So what we do is we put in our parameters, how high the person is, how old the person is, what their blood pressure is, and then we get fake data out of that. And it works really well as a technique.
Hey, Bruce, have you got your camera on you, Bruce? Yeah, yeah. Is your camera working on you?
Yeah, I don't. Yeah.
No, because you're frozen from. Yeah. No.
Here, I'll start my video again.
Okay.
I don't know why the video stopped.
Yeah, now we can't see you, so.
Okay, well, here, hang on. Let me go to preferences.
But it really doesn't matter because we've been following your slides, your cursor and everything, right? But except the image of you is kind of frozen.
Yeah, I don't know why it froze.
Yeah, but that's okay. Yeah.
Here, let me do this. Give me 1 second.
Yeah. Now we got a picture of you that's about 10 years younger.
You're not supposed to tell people that, you know.
But that's okay. According to Carl says it's okay. Just go ahead. Continue what you've been doing. We can, we've been following you really, really well. So.
Okay, give me 1 second. Where's my, you know what, I can't. I'm hitting on the video thing and Zoom is just not responding. Okay. So I'm gonna keep on and I'm gonna talk about one more technique that we're using in our research. Can you see me? Can you see it okay?
Yeah, I can see it okay.
Okay.
But right now the slide we are seeing is image captured with CycleGen, right?
Yeah, that's
okay.
Right. Okay, so here's the problem. The problem is we want to be able to have a person read an image off of a blood pressure screen. So they take a measurement, and what we want them to be able to do is take a picture of this so that they don't have to type in their metric. So this is when you're doing a comparison or a test, or you're adding a training record. We want people to be able to just easily take a reading off of any medical device, or it could be a thermometer, it could be any medical device. You want to be able to take a picture of it, get the data, and have the data automatically sent to the health gauge cloud so that your doctor can then see this data. So what we have to do is we have to automatically somehow pull out all these unwanted parts and just have the raw information. So you can see that there's many kinds of displays that are out there, different kinds of alignments, distortions that can happen. And so what we don't want to do is we don't want to just apply traditional computer vision, because the problem is that you'd just be sitting there twiddling forever, trying this, trying to reduce the background, trying to change the contrast, and then try to run it through OCR. It doesn't really work. So, and if you just apply CNN to it directly, you'd need 1 billion training records to get it to train to do what you wanted to do. So we tried the GAN approach, and we tried a particular kind of GAN approach. And remember, the value of the GAN approach is that these discriminators are constructed dynamically. They start out really, really small and really dumb, but then over time, when you give them lots of examples, these discriminators get really intelligent. And so what we decided to do is use the CycleGAN approach. And actually, rather than this slide, what I'm going to do is just talk about what CycleGAN is on this slide. So what CycleGAN does is it uses something called cycle loss or cycle consistency loss to train the entire network. So you start with some image. In this particular case, you can use this to take an image of a horse and turn it into an image of a zebra, or an image of apple and turn it into an image of an orange. And what we want to do is we want to take images of screens, of metric screens, and we want to convert them into nice, clean images with digits that we can then OCR. We don't have paired data, so this is the other problem with trying to use a CNN-based architecture. Is in order to get it to work, you have to have tons and tons of paired data. Using the CycleGAN approach, you don't need paired data. So this is one of the other advantages of it. So the way that this works is you train a generator. Let's over here, it's called generator, and it can take a start as its starting image, this X image, and it can generate a Y image. And then you train another kind of generator that goes the other way. It can take a Y image and turn it back into an X image, all right? And so this would be a horse, and then that converts it into a zebra, and then you get a zebra and you convert it back to a horse. And if you look at what happens in the entire process, you start with some image, you generate the secondary image, you then use that to regenerate back your initial image. And this loss, or this difference between your starting point and your end point, is what's called cycle consistency loss. And you use that to then feed back the error back through the network. And I'll just show you a little bit about how that works with the CycleGAN architecture. So we train this generator. So, and remember, in order to train a generator, you have to train a discriminator. So we train a discriminator. We then use that to generate these zebra images, and then we have a discriminator for zebra images, and then we can then generate, and then we have another generator to generate these horse images. And then so we do one side, and then we train the other side. We go the other way. So now we have another discriminator again for the same horse, but now the horse can generate a zebra, and then the horse can generate a zebra, which we can then discriminate on this side. So the advantage then is, if you look at what's happening, is we can apply this exact same technique to cleaning up images. So we start with some, we train a discriminator for these guys, and then we train a discriminator for these guys. Once I've trained a discriminator for the images, I can then start training the generator to go in this direction. And I can train a generator. Once I have a discriminator here and I have a discriminator here, I can start training a generator to go in the other direction. And so then I can do the entire cycle loss. So let me actually just show you what that looks like. So we start with an image, we go to this image goes to this image, and then this difference here becomes the loss. And then we can train it the other way as well. We can start with this image goes this image, and then we can train the loss on this side as well. So the results are actually really, really good. So the key idea here is that you're not actually building a discriminator by hand, you're growing an image recognizer. And the more data that you supply into the network, the more intelligent the network becomes over time. And ultimately, you can apply OCR to these images in order to read the data. And so we've applied this technique, and our results are really quite good. So one of the applications that we have, and this is a really useful application, is we're applying these images to finger-based PPG. We don't have enough wrist-based PPG data, but there's tons of finger-based PPG data. And so what we're working on is a way to convert this finger-based PPG data into wrist-based PPG data using the CycleGAN approach. All right, and so the last thing I'm going to talk about is something that we're doing with conversational agents. So here's what you'd like to do with a conversational agent. The conversational agent is something that you can talk to in order to get health results. And so what we've done is we've applied GPT-3 to do language translation. So GPT-3 is a general purpose language model that can be used for a variety of natural language processing tasks. It's based on the transformer architecture. So you get kind of a pre-trained neural net with GPT-3, and we use it to extract information. So here's some examples. Actually, these are examples on our website. So you can ask it a question, And GPT-3 is remarkably good at converting your textual statements into some kind of translation. It can even convert your textual statements into we could call them. This is called slot filling in this particular area of natural language processing. We don't have to use tokenizers. We don't have to use stemming. We don't have to do anything special with the data. We basically just run it through GPT-3. You give it some examples of what you want it to do, and it will then easily translate your input into these examples. In this particular case, what we're trying to do is allow users to tag their data or the health journals. We want them to be able to say, hey, I ran for a kilometer, or I don't feel very well. And normally a person would have to go through this, process of trying to tag their information using a graphical interface on a mobile device. But using this GPT-3 technique, we can just have a person just type their tag or even just speak their tag, and that data will then automatically flow into our database. And so this is kind of what the workflow looks like. We take input from the user. We then use GPT-3 to try to figure out what kind of input it is. Once we figured out what kind of input it is, we can then store it in the database, or we can respond directly back to the user. And so we have a few different intents that we can process using this GPT-3 technique. What we're also experimenting with right now is using GPT-3 Codex. So Codex is a particular tool released from OpenAI. OpenAI, they created the GPT-3 system, and they've built a variant of GPT-3 that can actually write code. And so what we're doing is using that to get our agent to write SQL queries that can access your data directly. So this is actually an image of our system, our HealthGauge system. You can see on the left, we have different panels where people can look at their data, but then there's a little chat screen where they can start chatting to our health coach, and chat about their health data. Actually, this is the team. I'll just introduce you to them. These are all graduates from the University of Alberta master's program, and they do all the heavy lifting, and that's it. So that's the end of my talk, and I'll leave it there. And if people have questions, they can just go ahead and ask away.
Yeah, so far I haven't seen any questions coming across, Bruce. So maybe just wait, give it a couple of minutes. Let's see. Well, it was pretty good, pretty informative. You guys are really into a lot of heavy lifting there, Bruce.
Yeah, we're doing some really interesting things. This isn't all, like, this is just sort of the core things that we're doing as it relates to the PPG analysis and the ECG analysis. We're applying these techniques right now to heart rate variability. We're applying them to AFib analysis, so basically irregular heartbeats and the various conditions that go with that. So that's a really interesting problem. And then there's many other conditions that that we're working with. Really the problem isn't so much the AI. The AI actually works pretty good. The problem is trying to get the health system to pay attention to all of the data coming off of the watch and use it in their health practices, right? So that's really the big challenge that we face as a company. Because, doctors, you go to a doctor's office and you see the doctor like once every few years, and you go in there and all he has is, maybe your blood pressure and maybe he weighs you and asks you a couple of questions, but doesn't know anything about your personal data. Whereas when you look at the rich sets of data that we have the sleep data, and we like all of your sleep data. We have all of your blood pressure data multiple times throughout the day. We have your activity tracking data, so we know how active you were. This is data that's really, really useful, and we're finding right now, working on finding lots of ways of coming up with health assessments that can help help individuals manage their health better, as well as information that doctors or other healthcare providers could use to assist people. So it's a really exciting time because the machine learning tools have gotten really, really, really good, and the processing power is out there. It's very, very inexpensive. It's available, and so we're really excited about the state that the whole industry is at. It's a good time to be doing this kind of work right now.
That's good. Yeah, I've got a few questions here, Bruce. How is the commercialization going on for your company and your products?
It's going well. I would say what we did was we went public. Actually, we sold most of our company to a public entity. The public entity raised a bunch of money on the stock market. So we have, we are in Canada, the US, and in Germany now. Our stock's available. So, and we're working through what was allocated to us. So I think that we're just now ready to go to market. We have about 4 major projects. We're working with, Alberta Health. We're working on various projects. We're working with the Fraser Health Authority in BC. We're working with actually health groups across Canada. We're doing something with, we're looking at wound management. We're looking at AFib analysis, and so there's we've got a project with a major university out on the west coast.
Yeah.
And that's actually, we've got about 200 athletes in that study. So it's going, I would say it's early days still, but there's just a ton of interest. There's also a lot of interest from research groups because and we'll start, we're going to start selling our kit to research groups in batches of 50 units or something like that. But it's early days still.
Okay. So the other question is, do you think the GAN technique has the trend of replacing traditional and completely? Is ANN completely? Do you know what that means?
SANN? I don't know what that is.
Just ANN, replacing and completely. You don't know what that is, eh?
I don't know. Artificial neural networks?
Maybe, yeah.
Are they going to replace? Should I look at the chat here?
Yeah.
Okay, so commercialization going. Okay. Do you think GAN has a trend of replacing traditional ANN? Well, okay, so GAN is an artificial neural net. It's a particular kind of artificial neural network. What GANs do for you is they give you a way to boost up the discriminator, right? Or the generator, right? Depending on what it is that you're trying to do. And you can boost up the discriminator to a level that is basically more intelligent than if you just had a whole bunch of paired data, right? So it's a really, really good technique. I've actually used this GAN technique in lung cancer recognition, where we generated a bunch of synthetic data for lung cancer, and we found that it gave us a 10% boost in the ability to detect lung cancer just by using artificial data, because again, it's hard to get all the data that you need to train up, the discriminator or the detector. And so it's not going to replace it. I mean, it is a kind of training technique. So
Okay.
how do you determine the NN model parameters? That's a really good question. We use some hyperparameter tuning. We also just kind of tweak it by hand. It's a bit of an art form. Hyperparameter tuning, so AutoML, or sorry, not there's a few AutoML. What are some of the other ones out there? But these are AI-based techniques that can do component analysis, and they can look and see which parts of your network are contributing more, and they can figure out how to add layers. I mean, some of them are pretty smart. They can add layers or increase the width of a particular layer, tell you how many epochs to run. So that's another parameter that's really important, whether or not what your max pooling should look like. All of the parameters can be tuned, and you want to use a tool to assist you in that. But you kind of have to have a good starting point. And for that, you just kind of have to have intuition, I think.
Yeah. Okay. So the other question is that how do doctors react to this kind of measurement technique?
Will it lead to people losing their job? Well, no, it's a valid question. I mean, I think that in the long run, AI is going to have a fairly big impact on health, but I think it's just going to make people smarter. It's just going to give people who already have, strong capabilities, better tools to do their work. So many doctors love this technique, but many doctors don't really know about it. So this is, a technique that's emerging right now in the world, using AI to do these kinds of estimates. It's being applied, not only in blood pressure estimation, but it's AFib analysis and, various kinds of cardiac problems. It's being applied in image analysis inside of, for X-ray images to do diagnostics or MRIs or other kinds of images. So AI is really making its way into the health space. And where we really see the big applications is in looking at the trends that exist in your own body, and those things are going to make you smarter. Doctors, they're not used to having this much data. I mean, this is one of the problems with working with the traditional health industry, and they don't even part of the problem too is they don't know what billing codes to use. And so that's another problem with introducing data. They don't know how to bill for it. They don't know what the billing codes are. And so we do have a challenge in getting this, AI-based analysis techniques into the health industry.
Okay. So the other question is for your projects, where are the funding coming from? Is it from the government or from VC or angel investors?
Yeah, no, so that's a great question. Some money does come from government in the form of grants to do a little bit of research. We haven't had a lot of government funding. Early on, we had a couple of, I don't know what I don't know what is a significant number, but a few $100,000, I would say. We also had SR&ED that applied as well, and that was extremely valuable to us. And then a few other studies. We're doing a study with ST Innovations, and that's going to be probably partially funded. So, but the vast majority of the money to kind of get the whole ball rolling came from friends and family. So we got friends and family money in, and then we started to get investors in that had a little bit more dollars. So these were experts, doctors a few doctors to put money into it. And then we went to the public market. So recently we sold a bunch of our company to AIML Innovations, and AIML Innovations went to the general public, and they raised lots of money. And
Okay.
so that's where we're at right now.
Okay. Okay. Now, I was just wondering if there's a way that we can show, all the good things that you're doing to the companies, the high tech AI ML companies operating in Edmonton or in Alberta, such as, like Alta ML. Are these people aware of what you guys are doing, or what about like Dark Horse Analytics? Are they aware of what you're doing?
Yeah, people know. I mean, it's a small community, right? And so
Right.
people are, presenting this, to each other all the time. In this community, we kind of know what each other are doing, not specifically, but we know in general. I mean, there's probably a good, hardcore, there's probably about 100 actually hardcore AI companies in the Edmonton area. I would say, maybe at least, more than a dozen that are doing really, really interesting work. But we don't really collaborate because the things that we do are very different. I mean, we should. I mean, that might be, something that we should spend more time doing is trying to figure out how we can, work together on some of these problems, because at their core, right, there's a whole bunch of similarities, but really when you take AI and you apply it and you get it to work, there's so many, every single network has so many differences that it kind of diverges fairly quickly. But maybe there's a good reason for us to be sharing more details with each other.
Yeah, I think one of the ways is obviously, through Data Management Association, right?
Yeah.
Conference, and same with Alberta AI. Several years ago, ran a conference as well.
Yeah.
On AI, right? So it is only through these conferences that folks like yourselves can showcase what you do, right, at these conferences and workshops and so on. I mean, at the end of the day, it's very synergistic for companies to collaborate, right? So that you can make a product even better and reach further into the different various sectors of the economy, right?
Yeah.
Yeah.
Yeah, absolutely. I think that's that's true. I mean, we've got to, how do we figure out how to do that?
Yeah. Like I said, one of the ways is hopefully, the in-person gathering will be allowed in a few months' time, and then we can go back to running our annual conferences again, right? At NAICS. Yeah. One question here.
I think the annual conference is great. We should definitely do that. But I think that, what we should also have, and with them, is we should have ways for organizations to kind of post their technology interests, so that if there's a way that we can collaborate, like if someone is trying to do this kind of a neural network, I'd be perfectly glad to go over and give them some pointers, if they were trying to do that. But I don't know, I don't really know who else is doing this kind of work. Or with conversational systems, for example, I love conversations. I would love to help somebody, who wants to apply GPT-3, but I don't know who's doing that and who'd be interested.
Right. Yeah, good points. Okay. So one question here. Will this device need certification from the government?
Yeah. So we're going through FDA regulation. So some of what I've shown is actually patented. And so I don't mind sharing it. The FDA is an organization that in the US that approves these kinds of devices. In Canada, there's Canada Health, and they approve devices. And so we, obviously we have to get all of these processes approved. The interesting thing is that organizations around the world realize that AI is very powerful, and so what they're doing is approving the software as if it was a device, if it was a physical device. So we're actually device agnostic. So we don't care what kind of device our algorithm runs on top of. It could run on top of on top of anything that generates the data. And so what we're doing with the FDA process is getting the FDA to, approve our software, as a device.
Okay. And one question is, typically, how long does it take to get certification from the government, like the FDA or through Health Canada, or whatever?
Well, if you've got all your ducks in a row, it can be anywhere from 3 months to a year, depending on a bunch of different things, right? So the typical, what's called the 510K. So if it looks like what you're trying to do is similar to something that somebody else did, then you can apply in the US anyways for something called a 510K. And usually if it's FDA approved in the US, you're going to get approvals around the world. And so that's why most organizations go for FDA approval first. If there's a very clear correlate to something that somebody else has already done, then a 510K is a fairly quick process. But if it's a little bit off, or if it's something completely new, then you have to go through this other channel called the de novo channel, and it can take much longer and be much more expensive. Your costs are running anywhere just on the FDA. And the FDA side of it isn't really that expensive, but you're going to have consultants, and those consultants, like an FDA process is going to run you 50, 60, 70 grand to get through an FDA process. But you have to have all of your ducks in a row before you go to FDA. So if you're thinking going that route, get an FDA consultant and get them to help you get ready. Then what you do is you go through this Q-sub process, which is sort of a fake approval process that FDA has set up, and then they tell you, here are the things that you have to do in order to get through the approval process. But it's a long, hard road for sure.
Yeah. It's like a mock exam, right?
Yeah, that's what the Q-sub is. It's a mock exam.
Yeah.
But this is not for the faint of heart. I mean,
yeah.
I can tell you that the regulatory part has been, the hardest part. One of the hardest parts of the entire company is kind of getting through, that regulatory nonsense.
Yeah, tedious, expensive, rigorous, right? Everything.
Yeah, exactly.
Yeah. Okay. Any other questions coming up? I don't see any coming up right now. It's about close to 5 after 8.
Yeah.
So, well, if not, I don't see any more questions. Oh, yeah, there's one more. Does your company have some sensors for mind reader or mental health?
No, we don't have any sensors for that. I think that's an interesting idea. I can tell you that there's a lot of research on something called HRV, heart rate variability. And so heart rate variability measures, how your heart varies over time. And you have two different systems in your body, the sympathetic and the parasympathetic nervous system. And these two nervous systems, they kind of fight with each other. And if one takes over, then, like if you get sort of aggressive or anxious, then your heart starts beating regularly. But if you're happy, then, these two systems kind of, they make your heart beat very irregularly, actually. So your heart rate variability goes up, and it goes up and down in certain patterns. And so there's a lot of information. There's a lot of research showing that by tracking heart rate variability, you can detect various kinds of psychological states. But that's about it for what we do. I know that there's a lot of companies out there that are looking at, putting electrodes on the head and, electroencephalographic EEG data. Let's call it, and that works. Some people have some good results with that, but that's not what we're doing.
Okay. All right. Okay. Okay. Let's see if there are any more questions. Give it a count to 5, like Carl said.
All
Okay.
right.
If not, then I would say okay, no question. All right. All right. Well, Bruce, thank you very much for the very insightful, informative, and educational session. And we thank you very much. And so, ladies and gentlemen, this concludes our webinar of October 27, 28. We thank you for your participation. And Bruce and I look forward to meeting you again virtually in the very near future. So good day and